In this presentation, we'll look at the analysis of transient optical signals using the OP740. The OP740 is a high-speed, multi-channel optical power meter. It has configurable sampling rates as fast as 8 microseconds. It is available with standard detectors of InGaAs for traditional telecom wavelengths and silicon for visible to near IR wavelengths. The OP740 has up to 24 channels of simultaneous sampling. This means there is no need to sync your signal across all the channels. The instrument's internal clock performs this function. The fast sampling speed of the OP740 satisfies military standard 1678-2A for monitoring high-speed optical discontinuities. The OPL740 software allows one to view all 24 channels simultaneously. Each channel can be enabled or disabled depending on the user's preference. Each channel can be set up in either relative or absolute power measurement modes, and there's a configurable pass-fail threshold to give the user immediate feedback if a signal is out of tolerance. To optimize the dynamic range of the particular test, each channel can be configured for gain settings, and one can view the power level for each gain setting. This allows the user to condition the optical source to a specific level within a gain to yield the appropriate dynamic range. The software allows the user to configure the sampling rate with fixed rates of 8, 16, 32, 64, and 128 microseconds. Or the user can enter any value between 8 microseconds and 10 milliseconds, and the software will select the appropriate sampling rate and decimation level to yield the proper effective sampling rate. The software also allows for high-speed data capture for an extended time. With the software, the data buffer is virtually endless and really only depends on the size of the computer's hard drive. With large datasets, the software can analyze the data for specific types of events. One can set upper and lower thresholds. The software will analyze the captured data and display events in a list. These events can be viewed on a graph and exported to CSV files where they can be further analyzed in Excel. Captured data can be saved and then loaded back into the software to perform the analysis. In this presentation, I will present some basic applications where the OP740 can be utilized. First, we'll look at the performance of a mechanical switch as well as a MEMS switch. We will then look at how the OP740 can be set up to monitor the insertion loss and return loss behavior of the optical signal when a connector goes through a mating cycle. Lastly, we will look at a common shock test and how to use the OP740 to capture and analyze the associated discontinuities. To analyze an optical switch, the setup requires an optical source to be routed to the input of the optical switch, and all outputs of the switch are routed into the OP740. The OP740 will be used to monitor the switching behavior. When switching from one channel to the next channel, one can see that the first channel goes dark. Then the channel that is being switched to becomes active for a short time. Then there are periods of intermittent light on the destination channel. The switching takes roughly 90 to 100 milliseconds to complete. To understand what is happening, one needs to look at how mechanical switches are constructed and controlled. Typically, the common port is aligned with the active port. When the switch changes channels, the common port is moved into alignment with the destination channel. To quickly get to the channel, the motor driving the switch needs to quickly move. This speed causes the common to overshoot its position, then return back into alignment. This overshoot alignment is shown in the optical signal by the intermittent light on the port. The OP740 captures and accurately represents this dynamic optical signal. In an attempt to look at a worst-case scenario, this 16-channel switch was switched from channel 1 to channel 16. Channels 1, 7, and 16 were monitored. The data shows that it takes about 300 milliseconds to fully transition from channel 1 to channel 16, but it also seen that channel 7 briefly lights up. As channel count of this switch would increase, the time to get to channels that are far away would gradually take longer. One can see that as the channel is changed from 1 to 16, the common port would briefly pass by channel 7 on its path to channel 16. This pass-by causes a brief power spike on channel 7. The high-speed data capture of the OP740 allows the signal to be seen. Sampling at a lower data rate would likely miss this event. Now, when looking at the performance of a MEMS switch when switching directly from one channel to another and skipping intermediate channels. In the above case, the system is switching from channel 1 to channel 3. It can be seen that there is a brief low power detected on channel 2. This blip is similar to the blip seen when the mechanical switch passed through an intermediate channel, except this blip is much lower. Also, the total transition time to go from channel 1 to 3 is about 10 milliseconds total. To understand the optical behavior of this MEMS switch, it helps to understand the internal structure. This MEMS switch isn't like all types of MEMS switches, but it is fairly common structure. The switch has a bundle of fibers that are incident on a small mechanical mirror. In the center of the bundle is the common fiber. This is the input fiber. Situated around the common fiber are the fibers for the switch channels. The switch steers the input beam of the fibers depending on which channel is selected. When incrementing through channels, the mirror steers the beam to each channel. However, unlike the mechanical switch, the mirror doesn't need to travel on a fixed path. So the switch can change channels and the mirror can move the beam directly to the appropriate channel without needing to pass the intermediate channels. In this case, when the switch is on channel 1 and channel 3 is selected, the switch goes directly to channel 3. The beam, however, partially passes by channel 2 on its way to channel 3. This results in a small power blip on channel 2 during this process. The OP740 captures the fine details of this power blip as well as the transition between the active channel and the destination channel. Even the damped transition to the destination channel is captured by the OP740. The result of this MEMS structure is a much more uniform response time when navigating across channels. Next, we will look at how the OP740 can help to analyze the mating properties of fiber optic connectors for insertion loss and return loss. To monitor the insertion loss and return loss of a connection, one can implement a 2x1 coupler. One input leg will be connected to the light source, while the second input leg can be used as a return loss monitoring leg. This return loss monitoring leg can be connected to channel 2 of the OP740. The single output port of the coupler will be used to connect the device under test. The output of the device under test is connected to channel 1 of the OP740 to monitor the throughput. Angled connections on the outputs and inputs of the coupler help to minimize stray reflections. First, the mating properties of the FCPC connector is analyzed. An FC connector is a screw-on connector. From the resulting graphs, one can see that for full stable contact, it takes about 700 milliseconds for the connection to reach equilibrium. During this process, the insertion loss and return loss swing wildly. These swings are due to constructive and destructive interference of the light waves in the small air cavity as the two connectors mate to each other. The width of the air gap creates constructive and destructive interference depending on the wavelength. When zooming in on the graph to see the point of mating, one can see that the IL swings between 0 and negative 0.6 dB right before mating. The return loss, however, swings between negative 9 dB and about negative 40 dB. The OP740 capturing resolution allows for this fast fluctuation to be completely captured and analyzed. Each interference peak and valley is fully resolved. Next, the signal behavior of a snap-in SC connector was analyzed. From the graphs, it can be seen that the total connection time takes about 2 milliseconds. Unlike the screw-in connector, the snap-in connector doesn't have a long period of insertion loss and return loss fluctuations. One common test on mated pairs is a shock test to see how well a mated pair can maintain connectivity through shock events. When selecting equipment for shock and vibration testing, one needs to make sure the equipment used is capable of producing reliable and accurate results. The optical source should have sufficient output power so that it operates within the range of the optical power meter. Ideally, the source is adjustable to maximize the dynamic range of the OPM when in range hold mode. An adjustable light source eliminates the need for costly attenuators in the setup. The optical power meter needs to have a fast sampling speed, and it must be at least twice as fast as the discontinuity that is to be monitored for. The military standard 1678-2A monitors for 50 microsecond dropouts, so it requires at least 25 microsecond sampling period. The OP740 samples at 8 microseconds, which is more than sufficient. The 30 dB of dynamic range that the OP740 has in range hold mode satisfies most of even the strictest requirements. This wide dynamic range allows for the discontinuity to be accurately captured without intermittent ranging hiccups. To set up a shock test to monitor insertion loss and return loss of a component, one needs to route a light source into one of the two input legs of the coupler. The second input leg of the coupler is connected to a channel on the OP740. The output leg of the coupler is connected to the device under test, in this case a mated pair, and the output of the device under test is connected to a channel on the OP740. In this case, the throughput or change in transmittance is monitored on channel 1 and the return loss is monitored on channel 2. Angled connectors are used to minimize back reflections. To reference the system, the mated pair is disconnected and the return loss is referenced on channel 2. This reference power will be associated with an open flat glass to air Fresnel reflection, or about 14.7 dB. The insertion loss is referenced by connecting the mated pair and referencing channel 1. The baseline for the transmittance of this measurement is 0 dB. Once the system is referenced, the software is put into capture mode, where the software is reading constantly from the instrument. Once in capture mode, a shock is induced on the mated pair. After the shock, capture mode is stopped in the software, and then the data is analyzed. When analyzing a shock signal, one is looking for three main parameters of an event. These three parameters are depth, width, and residual loss. The depth represents the maximum signal increase or decrease during the event. This value is usually with respect to the baseline. In this case, because we reference to 0 dB for throughput, then the depth is the maximum deviation from 0 dB. In most cases, these tests are only concerned with a reduction in signal power. On the right, the depth of the event is about 0.225 dB. The width of the event is typically the time that the signal dropped beneath the specifications thresholds. In this case, the threshold was 0.05 dB. The width of this dropout was found to be about 2.6 milliseconds. The residual loss is the power deviation from the power level before the drop to after the drop when the signal reaches steady state. The residual loss is usually measured with respect to the reference level. The discontinuity on the right is referenced to 0 dB, so the residual loss is the steady state deviation from 0 dB after the event. The event here has a residual loss of about negative 0.32 dB. Also of note, the residual loss can also be a gain as well. In many shock tests, throughput is analyzed and monitored. However, return loss can also be of concern. In this shock test, it can be seen that the return loss also fluctuates during the shock. For a couple brief moments during the shock, the return loss jumps to about minus 22 dB. This fluctuation could be the result of a slight separation of the ferrules and a brief loss of physical contact between the two fibers. After the event occurs, the fibers make contact and return to an acceptable return loss level. In conclusion, the OP740 is an ideal instrument for monitoring multiple channels for transient optical signals. One ideal application is monitoring for optical discontinuities and dropouts, such as for the military standard 1678-2A. With up to 24 channels of simultaneous sampling, there's no need to use an external signal to sync the signals. Everything is synced internally with the OP740. The configurable software allows the user to change the sampling rate and determine the length of the captured data. Since the computer is capturing the data buffer is as large as the computer's hard drive will allow. All data can be easily analyzed for simple events so that one does not need to sort through the data to find the areas of concern. If further analysis is necessary, data can be exported to CSV where it can be loaded into third-party data analysis software. Thank you for viewing this presentation. For further information, please contact Octotest Corporation.